Hello everybody, welcome to Intel and ActiveState's Accelerating Your Algorithms in Production with Python and Intel's MKL. We're going to get started shortly here. We just have a couple more people logging in. Alrighty, so my name is Ryan Perzik. I will be the host, which means my role is to sit quietly in the background and make sure everything runs smoothly. Speaking today will be Sergey Maidanov, Intel's Software Engineer Manager, and Tom Radcliffe, ActiveState's VP of Engineering. So without further ado, I'm going to pass the mantle off to Tom, and he is going to start us off. Oh. Okay, Tom, you should have the presenter role.
Okay, thank you, Ryan. As Ryan said, my name is Tom Radcliffe. I'm the VP of Engineering at ActiveState. My background is both in software and in physics, both pure physics as a nuclear and particle physicist, and applied physics in medical physics, computer-assisted surgery, and image processing. So I'm going to lead off the talk with a high-level discussion of algorithmic efficiency as I've encountered it over my career in those areas, and then pass things off to Sergey, who's going to go into much more detail about the MKL and how it is a better way of doing things, because it is. So overall approaches to efficiency include the high-level design of the algorithm or application, which can often buy us large factors of improvement without a huge amount of work. There's algorithm choice, which often gets the bulk of the focus in academic discussions of efficiency, but which I think personally is somewhat overrated. There are implementation details as to how we actually put our algorithms together, which starts to get us into the lower level parts of the code, and then there is the dive into lower level approaches, some of which are fairly obtrusive in our algorithms, and some of which simply sit invisibly behind the abstract layer of the high level language and do the work for us. There is a law, so I'm told, that you can't have a talk about algorithmic efficiency without citing a law about algorithmic efficiency. The one that people most like to cite is Newt's first law of optimization, which is don't do it. Newt's second law of optimization, for experts only, is don't do it yet. We also frequently hear the aphorism that premature optimization is the root of all evil. At least if you hang out with the kind of people I do, you frequently hear it. Which raises the question of when is optimization premature? And for me, this is fundamentally that optimization is premature if it happens before we have quantified performance. So no optimization without quantification is my first law of optimization. And by quantification, I mean two things. One is benchmarking, just finding out how fast the application or algorithm runs on normal data sets. That also includes an exploration of the variance in performance. If we don't understand the variance, particularly with the kind of Monte Carlo codes that I've done a lot of work with, we can have quite significant differences in performance from run to run just because of changes in the internal random number generator, what have you. So we need to understand the variance, or we run the risk of being fooled by variance when we implement optimizations. If we happen to get a fast run after implementing an optimization, we can think, oh, we've done something great, when in fact it's just randomness. The second aspect of quantification is profiling. This is where we want to find out where the algorithm is spending its time, which is rarely obvious from the outside. It can be very difficult to judge where the code is actually spending most of its time. I once worked on a large optical Monte Carlo that literally spent 25% of its time taking square roots of numbers that were close to 1, because it was renormalizing direction vectors after every scatter, which happened frequently, and it didn't have a very efficient math coprocessor back in those days. By writing some custom code for taking square roots of numbers close to 1, I was able to cut that 25% to about 20%, which meant, or about 5% rather. So it was a 20% speed up, which is a big deal when you have runs that are lasting for 5 days or more. That's a whole day in actual runtime. There's no way anyone would have looked at that code from the outside and said, oh, obviously it's spending most of its time taking square roots. Profiling is an absolutely necessary piece of quantification if you're going to start modifying code for higher efficiency. At the top level, there is a question of design, which fundamentally comes around to what is being computed and how. We are often led algorithmically by mathematical formalisms that have been developed with no particular attention to numerical efficiency, which is great. They give us deep insight into the problem that we're solving. But in many cases, particularly with optimization problems, our objective function may be more complicated than necessary to compute, and may use more data than necessary in its computation. So we should always be asking, do I really need to do all this work? Are there heuristics that can, or simplifications of the calculation that can make things run more quickly? An example of this is an algorithm I invented in the 1990s called pseudocorrelation, which was an application of Monte Carlo sampling techniques to a cross-correlation integral, which has been an idea that's been expanded. The most popular algorithm in this class is mutual information, which was developed several years later. But by taking just a subsample of the pixels in an image, rather than every single pixel, most of which didn't contain very much interesting information, I was able to get a factor of 100 or more speed up, simply by computing something that was closely related to what I cared about, but didn't use every single piece of data, regardless of its overall value of the calculation. So often having some kind of process to identify the information-rich pieces of our computation can be great aid to efficiency. The implementation details are often, did I skip a slide? I did not. Okay. The implementation details are often more important than the, there's a slide missing, right? That's okay. I was going to talk about algorithm choice, in which gets talked about a great deal. The normal thing is to talk about the order of the algorithm. We have order n algorithms, log n, n squared, what have you. And this is something that academics love because they have nice formal properties that we can talk about. In reality, it's often less important than you might think. There are many problems that come with a scale attached. If an algorithm runs sufficiently fast on 1 million data points, it may not matter very much that it doesn't scale well to 10 million or 100 million because we never see data sets that big. The work that I've done in biology in particular, I would frequently love to see data sets that were 10 times bigger than what I was getting, but the biologists could never produce them. So, although we do care about algorithm choice, it is often not a dominant factor in efficiency. And a well-implemented algorithm that doesn't have as high order or as good big O performance as a poorly implemented algorithm can often outperform it at a particular scale. The scaling will always take over in the fullness of large data sets, but that isn't necessarily what's going to dominate our actual performance. There are simple things we can do. One of the big ones in the Python world is to use NumPy arrays rather than Python arrays. NumPy arrays are a contiguous block of memory with some metadata associated with it. Python arrays are collections of Python objects. So a NumPy array can be accessed much like a C or Fortran array with very simple operations at the hardware level. and that can give us very considerable gains in performance. This is, however, the point where we start running into what Joel on software calls a leaky abstraction, where the underlying physical structure of the machine that we're running on starts to leak through the high-level abstract language over top of it. And we would like, ideally, that not to happen if we can avoid it. But we can embrace that if we want to as well. We can acknowledge that there is a machine underneath and we need to understand it and talk to it directly, which is the approach that Python takes, which is an extension to the Python language, which allows us to apply types to particular parts of the code and gives the interpreter enough information to effectively generate C-speed code out of the Python parts. The difficulty is we're no longer dealing with pure Python. We lose lots of Pythonic goodness in the process, and we've exposed ourselves to all of the issues that come with strong types. We have to start worrying about a bunch of things that Python itself used to protect us from. It can be a very useful approach if you have part of your algorithm which is numerically intensive and you can keep the Python tightly localized to that part. On the other hand, we can say, shouldn't there be a way of keeping the hardware layer below our high-level language abstraction? Shouldn't we be able to get something clever in hardware to use the hardware level capabilities to our advantage? And there might even be ways of transmitting high-level information down to that. There is a theory that says high-level languages should be more efficient than low-level languages because they have more information about the high level. The advantage of this kind of approach, which is the one taken by Intel MKL, is that it doesn't require any modifications to the pure Python code, the abstract code, that we would like to work with as algorithm developers. And the thing that you do need to use this is an MKL-enabled distribution of Python, like ActivePython, which has MKL built into NumPy and SciPy. So with that high-level introduction, I will now pass things over to Sergey to discuss the details of MKL and what it can do for our Python code.
Thank you. That was great introduction. My name is Sergey Maidanov, and essentially I spent all my life in coding numerical software, and last 17 years of that life was with Intel. On various projects, I worked with MKL, data analytics, acceleration library, and other numerical software products at Intel. Currently, I'm leading the Intel Python team, and today I will tell you about the magic behind Python that we put that makes Python super fast. And before I do this, let me start with some motivational part. What essentially motivates us to invest in Python and what secret sauce does come from Intel. This week, it's about this week, there was 20 years anniversary of the first Big Bang simulation experiments, and our colleagues at NERSC, they celebrated this date by conducting another simulation of this cosmic microwave background of our universe. But they did that at much bigger scale. They utilized more than 600,000 Xeon Phi cores to do this work. And interestingly, the Python was at heart of this simulation. You can hardly imagine how Python can scale to such a big number of cores. The quote below explains why Python is important for this type of research and why it is important in both laptop environments when scientists do prototyping of their code, but when it comes to real universe simulation, you really need to scale this model to thousands and hundreds of thousands of nodes. And this is why it motivated Intel to invest in Python and address some of these scalability challenges. I will talk about these challenges in a few moments. Let me also explain why Intel is doing this, because it's one of the frequent questions I've got. Why are you guys doing this? I will try to explain this on these two charts. The charts on the left, it represents some benchmarking on the mature AVX2-based instruction set CPUs, which is roughly 5+ years old technology. And the right-hand side chart, this represents recent technology AVX512 instruction set, which is basically Xeon Phi product family. On the left-hand chart, you can see the performance benchmarks, mostly linear algebra. And we compare performance of Python, NumPy and SciPy linear algebra performance relative to MKL, which is known to be the best mathematical library, highly optimized for Intel CPUs. You can see on the blue bar, this is what Intel Python engineering team did to optimize NumPy and SciPy. You can see NumPy and SciPy, they are close in efficiency to native MKL code. The black bars, they represent OpenBLAS-based NumPy and SciPy. And you also can see OpenBLAS delivers almost as good efficiency as MKL. So what's the point for Intel to do this work on Python side if OpenBLAS community does great job? The answer is on right-hand side. When it comes to for Intel to deliver new processor, MKL is already optimized for that new processor, unlike OpenBLAS and other open source software. That's why it is essential for Intel to deliver a full software stack, including Python stack, which is optimized from day one of the processor launch for this new hardware. And this is what we're actually doing. We're trying to help customers like NERSC not waiting 5+ years with their big bang experiments, but rather they can do this from day one of Xeon Phi launch. But what does really scalability mean? In short, the answer, the scalability means being efficient in parallelism. And there are multiple levels of parallelism available in modern CPUs. When I started programming, the CPUs were really, really simple. It was sub-1 MHz systems with instructions that retired in one cycle. Any instruction. You need to load the data, one cycle. You need to perform multiplication, one cycle. Everything is one cycle, everything is simple, everything is sequential. But the problems arise when you introduce something like floating point arithmetic. Floating point hardware is much slower than conventional integer and logic instructions. And hence, a floating point now needs to be executed multiple cycles. Same thing with memory loads. Over time, CPU frequencies, they rise a lot, unlike memory frequencies. And as a result, memory operations became slower and slower relative to compute instruction efficiencies. That all was addressed by introducing another level of complexity in CPUs, which is called instruction-level parallelism. In short, CPUs introduced multiple units and multiple ports, and they introduced pipelines where complex instructions were divided in simpler micro-instructions, and independent micro-instructions in these pipelines can be issued to different ports and executed on different units in parallel. That allowed essentially to overcome this issue. Your program is not stalling on slow instruction. You can execute in parallel other instructions while performing slower instructions. That's kind of instruction level parallelism. A simple example, you are performing data load. Data load is slow, but while loading the data, you can perform compute instructions in parallel on independent data. That's an example and common technique you're currently using to optimize your software for modern CPUs, any CPU. Another layer of parallelism introduced in modern CPUs was SIMD, which is called single instruction multiple data. With single instruction, you can execute in parallel this instruction on multiple data points. If you are thinking of performing element-wise array operation in a loop, with SIMD instruction, you can perform multiple loop iterations in parallel. That's an idea behind SIMD. The next layer of parallelism was introduction of multiple cores. You now are able to chunk your array in smaller pieces and execute calculations on each of these pieces in multiple cores. This is data parallelism. Or you can have your high-level application built of the graph of tasks, and you can execute on different cores independent tasks in parallel. This is task parallelism. So that's another layer of complexity. And like NERSC, they were executing these simulations on thousands and thousands of Xeon Phi based nodes. So another layer of complexity to exploit parallelism is multi-node parallelism. That all thinking should be behind how to make my code scalable on modern hardware. It doesn't matter whether your hardware is laptop or high-performance CPU. Fortunately, for Python programmers, for researchers and data scientists, many of this magic happens behind scenes. All this parallelism can often be exploited behind scenes. The simplest low-hanging fruit, we have numerical packages, NumPy, SciPy, scikit-learn, and we have native libraries from Intel, Intel MKL or Intel DAO. So what we can do, we can plug in MKL and DAO underneath NumPy, SciPy, and scikit-learn and get all this beauty of parallelism exploited out of the box without touching a single line of the code. The problem arises is sometimes there is not enough parallelism at the library's primitives level. Like your array is too short or matrix is too small to get enough parallelism on MKL level. Sometimes you need to go up to application level and find additional parallelism at the application level. The problem with that, if application level parallelism does not communicate with libraries level parallelism, then multiple threads become competing for physical cores, and you get oversubscription, which kills performance. So what we do as Intel, we bring technologies to Python, such technologies that you can still exploit parallelism on application level, not worrying much about orchestrating the lower level parallelism. And this is done through multiple technologies. I will not touch this topic in this introductory presentation. Same thing for multi-node. We accelerate MPI for Pi with Intel MPI native runtimes. Like Tom said, there are multiple technologies to get greater efficiency and parallelism through making Python and compilable code using Cython or JIT code with technologies like NumPy. Or you can use accelerated big data and machine learning frameworks, which already exploit lots of parallelism through these packages like TensorFlow. And like Tom highlighted, it's really critical before you jump in to optimization, and optimization is always a very big effort. You need to quantify how much performance you potentially get. And Intel invested in this side too. It created multiple language profiling tool, which is called Intel V2 Amplifier. You can use this tool with Python, with Java, with C, Fortran, and other languages, and essentially see your performance hotspots. Let me spend some time illustrating how we get this out-of-the-box performance with accelerated numerical packages. I'll have many slides showing performance data. So I need to have a brief introduction of what type of hardware we used in our benchmarking and software stacks too. Basically, the idea behind what we do, we want Python to work effectively on any type of hardware. Data scientists should be able to run code effectively on Core CPUs and then scale to servers on Xeon and Xeon Phi based servers. So lots of data that I will show you today were measured on Core laptop type system and Xeon, and then super many core Xeon Phi systems. And also when we do benchmarking, we're typically interested in several aspects of performance. The first aspect, do we perform well on serial code? In case essentially we're interested in per core efficiency. And then we're also interested in threaded efficiency. We see how this workload scales to multiple cores. The other aspect, we are typically interested to compare how Python package or Python library performs relative to native, respective native library. How linear algebra from NumPy or SciPy performs relative to linear algebra in MKL, or how machine learning in scikit-learn performs relative to native data analytics acceleration library, something like that. So lots of data that you will see today, it will cover all these aspects. And let me start with dense linear algebra. So on this performance chart, what we see, we ran few benchmarks, matrix determinant calculation, matrix multiplication, matrix inversion, LU decomposition on Core i7 system. And we compare efficiency of respective NumPy, SciPy routine relative to Intel MKL. And you can see on this Core i7 system, in most cases, NumPy and SciPy perform as good as Intel MKL, both serial and threaded code. This is what we essentially want to do. We do not want Python developers to spend their time in rewriting numerical codes in native language. We want Python numerical codes to be as efficient, not going from Python to something else. Same thing about fast Fourier transforms. Same Core i7 system. Blue bars still represent Intel, Python, NumPy, and SciPy relative to MKL. And again, you see close to 100% efficiency on serial and threaded FFTs, 1D, 2D, 3D, in place and out of place. All these combinations deliver great efficiency, as efficient as MKL. The red bars, this is stock NumPy, pip installed NumPy that comes through PyPI. You can see it performs relatively well on 1D serial code, but when it comes to scale the code, especially in multi-dimensional FFTs, the efficiencies are not really high. That's why we optimized NumPy and SciPy FFTs. The next example is NumPy UMath functions. UMath functions you can think of performing element-wise operations on array, like element-wise addition or multiplication of arrays, or element-wise transcendentals on array elements. On the left-hand side, you see some basic arithmetic operations. And really, these are so atomic that there is no enough parallelism in these atomic operations. That's why they don't scale much relative to transcendentals. Transcendentals, these are much more complex operations, and hence they exploit more parallelism opportunities. This is Core i7. Let me show you the data for Xeon. On Xeon, we see much better scalability. This is more powerful CPU with more cores, essentially with more caches. That's why you see even basic arithmetic operations start scaling well. Still imperfectly. Theoretical speedup is, if I'm not remember, it's 44 cores. You can expect 44x improvement. In theory, you see only 10x. But for transcendentals, you see huge speedups because optimizations that we done for UMath functions, they exploit this parallelism coming through MKL VML functions, vector math library functions. And Xeon Phi, even greater performance speedups. Not as big on arithmetic, and again, there is not enough parallelism in these atomic operations. So with that, the really question, if I don't exploit enough parallelism on atomic level, can I exploit this parallelism on application level? Let's see some proxy application that uses UMath functions a lot, and we'll see how it scales. And for that, we will use the famous Black-Scholes formula. Essentially, we are evaluating European-style call and put options, and we do this with analytics formula, which involves lots of exponentiations, cumulative normal function, logs, square roots, etc. So this is really compute-intensive, arithmetic and transcendental intensive, but it also stresses lots of memory. You see many parameters. Essentially, to compute call and put option, you need to supply a bunch of input parameters. That stresses memory a lot too. That's why I really like this benchmark. It illustrates both efficiency of using vector performance units and memory. This implementation uses NumPy UMath operations. If we run it on Core i7, you see the behavior is as follows. On small problem sizes, which is on the left of the chart, there is not enough parallelism to scale. The scalability begins only when the problem size increases to some level, and it grows, efficiency grows until saturation point. And the saturation happens when problem size increases to the level it starts draining cache. Core i7, this is laptop type system. This is doesn't have lots of cache. That's why it really doesn't scale on really big problems. But it's good enough to run on smaller data set on laptop, to do some debugging on a laptop, and then scale to Xeon and Xeon Phi. Let's see the performance on Xeon and Xeon Phi side. Again, on small problems, it doesn't scale, not enough parallelism. But on big problems, we see nice scalability to really, really big problems, and even better scalability on Xeon Phi. That gives you a flavor how even with these atomic optimizations that we bring to atomic UMass level, your application still scales nicely. Maybe imperfectly, but still scales. So we're still going through Black-Scholes formula, nice benchmark to illustrate essentially the alternatives you have during the implementation of the Black-Scholes formula, and being mindful in selecting the right alternative, keeping in mind all this motivational part about efficiency, instruction level parallelism, SIMD, multiple cores. What's the right choice I have to make on Python side to implement the most scalable code? The most naive approach is to use plain Python, no NumPy arrays, just a simple loop over options over problem size, and do element-wise operations. That's totally unscalable solution. You do element-wise scalar, scalar, scalar operation. There is no parallelism to utilize SIMD. There is no exposure to multiple cores. That's why on the left side, you see flat performance profile. It doesn't scale. Second variant, this is the variant we already considered. This is NumPy UMass functions. The difference is that now P, S, T, and all other variables, they are NumPy arrays. So when we perform P over S, it means we do element-wise division, P by respective S element. And we put result in temporal array, and then we compute log of this temporal array. So working with arrays allows us to exploit SIMD and exploit multiple cores if the problem size is big enough. This is what we see on the left-hand side chart. The problem scales nicely. And I bet you put the same, if not less, effort in coding in plain Python and in coding in NumPy arrays. Same amount of lines, same complexity of the code. But if you are mindful a bit, you can get much better performant code. One more variant is using a package called NumExpression. Essentially, it does the same thing. It works with NumPy arrays, and you can supply as a string, text string, the expression to evaluate, and that evaluator will create the expression graph and will execute the graph in parallel if there is enough parallelism. That's why you see about the same performance as in the previous variant. What we coded with NumPy NumExpression does essentially the same thing. What limits the parallelism is this atomicity. We still have very atomic expressions like log over p of p over s, something like that. They're too atomic to scale well on big number of cores. So with some additional thinking, we can re-implement num expression in something like this. By doing the same thing, the only difference is that small chunks of expressions, they're combined in big expression. And now operation is not too atomic, and num expression can chunk this data in smaller chunks and execute this big expression on multiple cores. And you see much better scalability because you now expose parallelism on application level, specifically through num expression parallelism. Okay. What if I use Python? The code size is still manageable. Yes, you need to do static typing. That requires additional care. And you also need to add some additional decorators to enable compiler vectorizations. And if you then compile this Python code with Intel compiler, which can do automatic vectorization, which will insert OpenMP pragmas, you will have scalable codes with much better performance. Let's see how close this Python performance to really native implementation. We completed C++ implementation of the same Black-Scholes formula. It delivers 4,800 million options per second speed with C++, but really comparable with Python, which is 3,400 MOPS. If you don't want to spend time in Python, you can still get reasonable performance with num expression. Or you may decide, I'm okay to use NumPy arrays and UMass functions too. It's all your choices. What's important to be mindful in thinking where the parallelism is hidden and how to unlock this parallelism. I will spend a few moments on machine learning because Python is a great tool for data scientists, and data science, modern data science, is impossible without machine learning. I will tell you briefly what Intel team is doing to accelerate machine learning and what technologies we bring here, and show some nice performance charts like this. So when you talk about machine learning with Python, the first package that comes to your mind is probably scikit-learn. What we did, we optimized key scikit-learn algorithms using MKL and using data analytics acceleration library, DAL. And you can see the light blue bars, they represent scikit-learn efficiency from Intel optimized scikit-learn relative to DAL. In many cases, it's close to 100% efficiency. Unlike stock scikit-learn, what you get through pip scikit-learn, pip install scikit-learn. Why is it so? So let me spend a few moments about DAL. Intel DAL, this is Data Analytics Acceleration Library. This is C++ library, heavily optimized for machine learning type of workloads. It employs Intel MKL at kernel level, but it really brings much more performance, extra performance, by dealing with data sets which are specific to machine learning rather than data sets specific to HPC, and MKL is more optimized for HPC-like data sets. So DAL, this is powerful low-level API, native library, C++. We built multiple language bindings for DAL, Java, and for Python, this is PyDAL, Python interfaces. Unlike scikit-learn, this library allows you to deal with much more complex machine learning scenarios, data analytics scenarios, like working with non-homogeneous data, working with missing data, with noisy data. It allows you to implement streaming analytics, like online algorithms, or work with distributed data sets. So this is really powerful low-level library to build the most complex scenarios. It's optimized for Atom processor, for Core, for Xeon Phi, for full range of CPUs. So you can perform really bare metal efficient analytics on various types of devices. Scikit-learn's beauty, it's really nice API, very simple to use. The downside of it operates only with homogeneous data, with arrays of floats or doubles, essentially, or matrices, and only for data which is in memory. You cannot deal with really huge data sets using scikit-learn. So PyDAL is relatively low level and more complex for programming, especially for data scientists that needs quick prototypes. That's why for data scientists, we introduced another level of abstraction, even higher level APIs, scikit-learn-like APIs for PyDAL, which are called DAL for Pi. And these are really new and hot. We released this just a few days ago. You're probably the first who know about this. So what I really encourage you is to try out this and see how simple it is. It's still capable working with non-homogeneous data, with online and distributed analytics. Let me show you something else. This is an example of DAL for Pi APIs. With 4 or 5 lines of the code, you can do clustering. In our example, we're processing data sets which are stored in memory and loaded from CSV file. One line is essentially loading the file in memory. Then second line is initializing centroids. And one more line is performing compute on these centroids to refine clusters. 3 lines of the code. And 3 or 4 lines of the code to do the same thing with MPI distributed workloads. We have multiple CSV files on multiple nodes, and then we tell DAL, here is the list of these CSV files, and I want these k-means to run in distributed mode. And we run MPI. That's it. Very simple way to scale the same application from your laptop to many nodes. So currently, you can install this package and try it out. It's not part of any distribution yet. This is technology preview. If we get positive feedbacks, then we'll consider including this in products and deliver to the market. Let me spend 2 more minutes in telling the story about broad enabling Python ecosystem. What I've told you, it's not only about Intel's own distribution. Intel created own distribution only for the reason that we want, from day one of new processor launch, customers to have ability to download Python, which is optimized for the CPU, and run these workloads like nurse crowns on very efficiently. But our objective essentially is to enable all these optimizations to the broad Python community. For that reason, we work with multiple vendors such as ActiveState and helping them to enable these optimizations in their respective Python products, so their customers benefit from this beauty of Python code scalability. We also put this individual optimized packages, NumPy, SciPy, scikit-learn, etc. on Anaconda Cloud, and Intel has own channel on Anaconda Cloud. You can essentially install these packages. Or these packages actually come with build recipes, and these build recipes, they contain these optimization patches. You can simply get the sources of these patches from build recipes and apply in your own project if you don't want to deal with Conda install, for example. Or what else do we do? In parallel, we work, of course, with NumPy, SciPy community, scikit-learn community to upstream these optimizations to their respective main GitHub projects. It takes time. Sometimes it takes many months, if not years, to get these patches accepted. That's life. And the last but not least, these nice runtimes, such as Intel MKL runtimes, Intel DAL runtimes, they are now packed in Conda packages as well as wheels, deep installable wheels. So we are working to make these packages available on PyTI. So every Python community developer can use these packages to use it in own project, to scale own project using MKL, DAL, and other solutions. With that, I essentially conclude my part of the talk, and we are ready for Q&A. Thank you.
That's great. Thanks, Sergey. That was extraordinarily informative. And as I mentioned before, the MKL enhancements are baked in to ActivePython. And if you just download it, you will get SciPy and NumPy with those capabilities as part of the distribution. So I guess we do have some questions.
So we have a couple of questions assigned to Sergey right now. So Sergey, if you want to tackle
that. Can you read it for me? I have really...
Would it, so a question from Michael, would it be not too far off to guess that Intel might produce a version of processor enhanced and equipped with additional instruction set based on MKL?
Actually, this is what happened when I worked on MKL team in my life. We start working with hardware architects long before essentially CPU design starts. MKL team works with CPU architects, provides representative workloads, and they provide some recommendations for new instructions. And some of these instructions were really implemented in modern CPU hardware. I don't see the reason why it shouldn't continue this way.
All right, thanks, Sergey. So if there's any other questions, please post them in the Q&A chat on the side. In the meantime, one question that's come up is how to access the recording for this webinar. All of the, everyone who registered will receive an email in the next day or so with a link that will allow them access to the recording and the slide deck. So are there any more questions for Tom or Sergey? Maybe a few more. Nothing. Oh, we got one more.
What license is DAL for Pi?
Yeah, Tom, do you?
Yeah, Sergey, there's somebody asking what license is DAL for Pi?
DAL for Pi is currently evaluation license because this is not yet product technology. You can use it to evaluate. And as soon as evaluation completes successfully and we decide to productize this, then it will be available. All our optimizations, all our packages are free. You don't pay for it, and you can freely redistribute this. So if we decide to productize DAL for Pi, it will be the same story, free DAL for Pi and freely redistributable. redistributables. I'm sorry.
That's great, Sergey. Do you have any sense of what the timeline for productizing Del for Pi might be? I realize that's probably getting out of your area.
Only basic principles. We want to solicit enough feedback from customers about usefulness, and if the feedback is positive, then that's trigger for us to productize. So far, we have really see good interest. It's live only for a few days, and we already have dozens of downloads. That's why I encourage you, try it out, let us know, scripting@intel.com, and that will be helpful for us to make decisions.
Cool. Yeah. So people should be downloading and installing. We do have a question about how to integrate with different Python distributions. As I said, this is pre-integrated with ActivePython, both 2.7 and 3.6. And Sergey's slides had some information on alternatives to that. So the simplest way is download ActivePython, your preferred version, and get it that way.
All right, Tom, I sent you one more question there from Julio.
Okay, let me see if I can see it. It's some public repository with code showing 101 examples of how to use those capabilities you showed us. That's maybe something Sergey can answer. We do have a lot of code recipes on the ActiveState GitHub, and a great deal of this, one of the nice things about MKL with NumPy and SciPy is the examples are just NumPy and SciPy. It's a very unobtrusive engine to drive things faster. But Sergey, are there example repos that Intel maintains?
Sure, and that's a great question. Thank you for reminding me to let you know all benchmarks that I showed on slides, they are on public GitHub repository, github.com/IntelPython. Find benchmark subfolder, and you can get all these benchmarks and run it yourself.
That's great. Intel Python at GitHub.
Yes, and some additional details, how to run these benchmarks, you can find it on Intel Python forum, software.intel.com/IntelPython, something like that.
Excellent, thank you.
Great, do we have any last minute questions?
Going once, going twice.
All right, well that concludes our webinar for the day. Everybody who registered will be receiving an email with a link that will direct you to a recording of this webinar so that you can access it at any time. That email should be going out in the next couple of days. And on that note, thank you for attending and have a good day.